Computer. Okay.
Well, hi everyone, I'm Shanti. Um, I'm currently a research fellow in UCL. Today we have the pleasure to host Zhe Yang from Zhe Yang University of Technology. His expertise is in computer science, and he finished his PhD in Zhe Yang University, and then finally become a lecturer in Zhe Yang University of Technology. And today his presentation is mainly about how to use set at home sensor. This is my words to describe to detect the early stage health risk of older people, specifically to in terms of our gerontology topic. So I think now we give the microphone to Joe to give us a short introduction about how we can understand this field and how it could be useful, or how we can further collaborate in this field. Yeah.
Yeah, thank you, Shinki. I will share my screen. I so am I sharing my slide right now?
Yeah, but we see the presenter version. We see the desktop version of it. It's not full screen yet.
Like
Yes, yeah, no,
like
perfect.
this?
Yeah,
Okay.
yeah, perfect.
Okay. 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 Thank you for the hosting of everyone, and I'm very glad to be here to present my work about the private preserving ambient assisted living location and activities. My name is Zhe Yang, and right now I'm a assistant professor and lecturer in Zhejiang University of Technology, and I'm in the College of Computer Science and Technology, and this is my email address. And sorry again that half of my presentation is in Chinese because this is a previous talk I have gave it to the another university, but I have already modified it to the English version. Some of it, but I didn't make it all the slides, so I will try to translate it when I'm presented. Okay, so first, this is the table of content of today's thing I want to show you guys, and first introduction, second indoor localization, third the human activity recognition, and also the summary. So first is the introduction that why I focus my research on the localization and also the activities of human. So the background is that the aging population presents an increasingly severe situation, and how to address this issue remains a global challenge yet to be solved. So you can see from the figures that there are many chronic and non-communicable diseases that continues to grow, like the diabetes and also the mental problem, and also some Parkinson disease, and something that it's hard to detect right now, and it's hard to recover from a very short time. And also something like injury caused by the by incidents such as falls can be fatal for the older adults. So ambient assisted living AAL is an European research funding program aimed at improving the quality of life of older adults and advancing healthy aging technology. And it tried to address a wide range of issues, including the chronic disease management, daily activity assistance, and support for informal caregivers. Okay, so you can see that it tried to introduce the electronic things into our try to make them to fit the tempo of the modern society. Okay, so my key focus of my research is that human activity recognition, the HAR, and also the behavior analysis. It helps to analyze the lifestyle patterns and manage health and prevent dangerous incidents like fall. So I try to sense that what you're doing right now. For example, are you drinking water, or are you going to the toilet, and are you sleeping right now? And also, it detect that if you fall down, and it will like make alarm to your family. And the other aspect is the accurate location that essential too for identifying the activity. It allows personal habit to be mapped to specific living areas and ensure that the person location is known during emergency, thereby facilitating health monitoring and also the safety assessment. These two figures at the bottom show that in one floor plan of the of somebody's house, and you can see that the trajectory from like 1 day and also like 1 week and 1 month. So indicating that if something happened that abnormally, I can detect it from the location. But there's some challenges that because location, for example, how to utilize highly available low-risk positioning resources in ambient city living scenarios and improve the positioning accuracy through multimodal, multi-source information fusion is a key problem. And for the activities, there's a problem about the cross-subject recognition. You see that for different two people, their patterns of their same activity in the same time is quite different. They have their own pattern, but actually they're pointing to the same activity. So because it's limited by the size of data set, we cannot collect all the people from all over the world, and the size of the data set is limited, and it's easily affected by variation in body proportions, personal habit, and also how the device is formed. Maybe someone like to want it like the smartwatch from the left hand or the right hand is different. So and also a big question is the privacy. Nowadays, not only the video data and also the audio data will leak the identity. And the point cloud. So the point cloud itself will have something to leak, like the body information or the activity that are very sensitive. Okay, so the first thing is the multi-source fusion location service, and so the location-based service is about public safety, including the emergency response, firefighting, rescue, and also the airport security, and also not about safety, but services like the hospital navigation. I want to find the clinic that I want to go to, and also some install advertisement pushing, and also virtual reality games, and the problem in the indoor localization is that although the global navigation satellite system and also maybe GPS global positioning system, they are commonly used outdoors, but indoor accuracy is insufficient and also often unusable. And sometimes when it something happen like the fire and maybe the infrastructure, including the Wi-Fi anchor, Bluetooth anchor, and also near field communication anchor, that is not in use at that condition. So how can you locate the people inside the house is a question. Okay, so if all the thing is not useful at this condition, we might just use the inertial navigation. That is the you can see from the bottom of the figure that I can starting from the very beginning location x0 y0, and I calculate my step length is the L1, and I can get the theta I, that is my direction. Maybe you can call it the heading or the yaw of my heading information. So I can calculate my current position. Okay, so this is just from the inertial sensing. If I have the infrastructure like the Wi-Fi and also the Bluetooth low energy, the BLE, and also near field communication NFC, and the ultra wideband UWB, these are all the radio frequency based localization. They use the radio frequency signal, and I can use the anchor, or I call it maybe baseband that I can set previously in my house or in the other indoor scenarios. So the radio frequency base, also called RF base, is using the information from the range that what is the range from my point to the baseband. So I can detect the angle of arrival, and I can also detect the time of arrival to detect the distance, and also the time difference of arrival. This is the most accurate way that I can detect the received signal strength. That is actually in your house you also have a Wi-Fi router, but sometimes you might see the signal is not good. So when you're watching a video or playing a game, you're not in a good condition. So this is called the receive signal strength. This one is actually related to the range of your place and to the baseband. And the other thing is the channel state information from the modern baseband like the Wi-Fi signal. We can use the physical layer information that to analyze how they scatter and the reflect in and how they scatter and reflect in an environment, and estimating the target location by mapping the signal distortion to specific spatial coordinate or propagation models. Okay, so you can see from the left figure is about how can I use the receive signals range to get the range, and how can I get several range and I can get my location using the like triangle location algorithm. And the right, the Wi-Fi transmitter and Wi-Fi receiver, and between them I have a field, and whenever the person, a moving human, is like CSI, the channel state information. So from the information, I can recover the trajectory of the people. Okay. So based on this, we have already implemented some localization system using the Bluetooth anchor baseband from the hospital and other places like this. Like this one, we use it. We use the inertial sensing and also the BLE anchor to locate the people, using the particle filter to get the accurate pedestrian depth reckoning. And we also in Hangzhou, where the Zhejiang University is beside the West Lake. There's a very big area, just like the Tokyo Shibuya area. There are many people there in the crossing. So we developed one product that's using the not only the GPS, but also the Wi-Fi detecting, that I can detect the Wi-Fi signal from the shopping mall surrounding, and I can locate every security, and I can get their trajectory. And when like big festival or something happen, some accident happen, that I can locate every security. I can manage their like trajectory or something. And this is one thing that I can locate the property of the hospital, like the where the where the nurse is and where the patient being. So I can locate everyone because that in the COVID-19 situation, that it's not good to let the COVID people to get outside the hospital. So the indoor localization system. And another way is that I don't use the infrastructure system like the Wi-Fi and also the UWB and the Bluetooth. I can just use the self motion tracking. So the basic idea is that I can either use the visual based, the camera based method, or I can use the non-visual based method. So first, I should start from the visual based. So the SLAM, the simultaneously localization and mapping, and also the SFM, the structure for motion, they are all the very common method for the robot, like motion planning and also in the modern robot vision. So it's calculating the angles and also the moving trajectory from two different images. So I can get the triangulate information. So I can calculate the moving. So just like this. But the problem is that it will have some privacy issue because you are always opening the camera. So if you recording the other people or you're recording your indoor activity, it will leak some privacy information. And also, recording the images are always very power power the power consumption is very high. So sometimes it's not a good solution for the elder people that are living alone in their house. Okay, so another thing that we can recover the privacy information is that we just use the inertial navigation system. It's based on the inertial measurement unit called IMU. So it's consisting of the accelerometer and also the gyroscope and also maybe the magnetometer. So if I get the information of the acceleration from three axes and also the gyroscope that indicating the rotation velocity from three XYZ coordinate, and also I can get the information of the Earth's magnetometer information, so I can get the result from the pedestrian depth reckoning. So, just like I said from the beginning, the starting point. So I can like this. You can see that I can use the previous location and also my step length and also my step heading, and I can use the cosine theta to multiply by the step length and I plus to my previous coordinate. But the problem is that this is not a absolute location algorithm. This is a relative location algorithm. So you can see that you are always using information from the previous state. There's no global calibration information like the Wi-Fi. I know that Wi-Fi anchor or Wi-Fi baseband is always at that place. But when you're using the inertial navigation system, you have the inherent drift from the sensor, and you will accumulate the error that when you're going a very long time or very long trajectory. So there's a statistic result from a paper that it can have when you travel for maybe like 100 meters, you might have maybe 15 degrees of the maximum heading error. So this is a very big number. Okay, so my research when I candidates is the infrastructureless indoor localization system that using the inertial navigation system, but having some calibration from the environment information. So the first thing is that I using the camera to detect the visual gyroscope, and I also use hybrid filter system to merge the information from the three sensors in IMU, like the accelerometer, magnetometer, and also gyroscope, and I get a very stable estimation of the heading. So if I get a very stable heading information, I can have a very stable localization information for a very long time. And this is the architecture that I merge all of the sensors from the smartphone, and I hold the smartphone, and I open up the camera. So you can see that this one actually have a privacy issue, but it's the beginning of my PhD research. So I later having something to improve this indoor localization system. This is the beginning that yeah. So the other way to improve the localization area is that I can use the ambient information. For example, and if I am in the corridor, that my heading is actually limited in uh, some degrees of the heading bias. So I can use the particle filter that if I randomly sample the particle around my localization, I can let the particle that lies in the inside the wall or the invisible area that I cannot walk in, that I set the weight of this particle to 0, and then I can make my heading more accurate. And also sometimes I can assume that I just having the corridor in the just the east and west direction, and also the north to south or south to north direction. So I cannot have a third direction that I'm going to inside this building. So this another assumption in some area. And also you can have a database of the images that you already recorded in your previous visiting to this place. So I can register my current image to one of the image in my database, so I can get the reference, so I can calibrate my localization information. And the last thing is that I'm focused on is the loop closure detection. So loop closure detection is that I detect whether I revisiting the same place I previously already visited. Check the loop closure, I can merge the trajectory to a very accurate location. So this is just like the figures show that I detect the images and see that if I already have the same image in my memory. But the problem is that at the right figure, you can see that some challenges might happen when you have different view angle. And also maybe there's some pedestrian or moving object that come into your figure, and it will have some outlier of the image feature, and also something about the different season and different time of the day or at the beginning of the day, the features can be very different. So these are the challenges that how can you detect the image to be in the same location. So I detect two algorithms to let it more accurate. So you can see that I divide the image to different small grid, and I detect each of the grid to have two different score. One is the structural similarity score. This is about that if I have in this similar image looking, similarity. This is about that if I have in the same pairing of different locations, just like the upper left, the upper right, the bottom left and bottom right, just like the foreground, what is the candidate that being the most similar to my images, so I can get the final score to find the best match of the current images. So in this way, I can have a very good loop closure detection. And also in this way, I can put every image in different computing engines like the GPU, so I can speed up the procedure. And another way is to detect the histogram of the downsampled grayscale images that I can have a statistic information, and I using the hashing algorithm to quickly detect the candidate that being the loop closure pair of the current images. Okay, so I having the very fast inferring time, and I also have a equation to making the algorithm more general. Like I can divide it by the factor. This factor is it's the minimal similarity between the two different images in the current database. Okay, so this is the research that about the loop closure. So if I have the loop closure information, I can reclose the trajectory that it may have some accumulate error from the inertial sensing. Okay, so another way is that to make the loop closure more accurate is to using the deep learning. So I use the CNN to check if the current feature of the image is similar to the previous visited place feature. Okay, so it's also have an improvement of the accuracy. And this is the another extended work of the thematic detecting of the road, so I can know that which area is the road plan, which area is the building, and I'm using this as a deep learning descriptor of the images, so it again improve the previous loop closure detection. And in this way, I can make a map of the thematic map that each of the pixel in the 3D coordinate that can be indicating as one of the thematic object, like the road, like the tree, like the building, or like the other very important information when we are driving. Okay, and you can see that from the previous research that I'm start from my PhD, there's something very about the privacy, because I'm always using the images from the camera, and I'm always having to put the camera in front of me to make the camera just pointing to the direction when I'm walking. So I'm thinking about that. Can I use some like privacy preserving technology that also for the ambient information to calibrate my accumulate error from the inertial navigation system? So I use the binary sensor that came from the home assistant sensor, just like the door sensor is using the magnet to attach on the door. So when it open, it will have a signal of 1. If it's closed, it will have a signal of 0. And also the other binary sensor is like when you open the oven or when you close the oven, it will be like 1 and 0. When you open the television, when you close the television, it can also be 1 and 0. So this 1 and 0 we can detect because they are all connecting to the internet or the local network in your home. So these are all the binary sensors that calibrating my indoor localization error. So one of the binary that I found is very useful is the ultrasound from the appliance in the in everyone's house. So this is because that in the basic circuit system, we have the transistor and also we have the capacitor. So these two component in the circuit, when it working, it will have a very high frequency of vibration because you are always charging the capacitor and you always discharging the capacity. So the frequency of the charging and discharging is relating to a sound of the same frequency. So I use the microphone to approaching the different appliances like the printer, the air conditioner, the lamp, and also the air purifier. So I can see that in the frequency area, I can see a very significant pattern for different appliance. So there's no appliance I cannot detect anything, but if I'm approaching to a lamp, I'm approaching to a printer, I can detect that yes, I'm here. So this is one way I can detect the location anchor, so I can locate myself with this information. And also, when I changing the working mode, just like the lamp, when I'm changing 0 level, 1 level, 2 level, 3 level, the pattern can be quite different. Okay. So I merge it to the basic inertial navigation system, including the information from the gyroscope, magnetometer, accelerometer, and I have a graph optimization algorithm to merge the step length estimation and heading estimation, which will have a result of the PDR of the pedestrian dead reckoning, and also I have the reference from the appliance that it indicating what is the actual position when I'm approaching some appliance. So I can use the graph optimization to get the update location, and this is the illustration of my system that I can use the microphone from the smartphone and also the inertial sensing from the smartphone. So I will not making my smartphone always pointing to the direction I'm walking to, and I can put it just in my pocket because the sound it can have the same thing even if even if I put the sensor in my bag and also in my pocket, I can have the signal. So with this all information, I can calibrate the accumulate error from the inertial sensing and make it more accurate. You can see from the figure that I'm walking a very long way, like 1 kilometer in the indoor area, and finally I got a very stable and also a very accurate localization trajectory. And another extension is that because we cannot make every appliance to making a sound when it is working, and also when it's not working, it has no sound. So how can we extend it, the binary sensor anchor to a more general cases? So I use the Bluetooth anchor that is not previous set in the ambient, but I actively like dropping it in half of my way. So also I'm using the inertial sensing, but in this case I using the binary anchor that Bluetooth anchor that I can detect if I am in the area. The basic idea is that I making the strength of the transmitting of the signal to be at the lowest working mode. So I can only detect the Bluetooth signal from within 1 meter when I'm approaching to the anchor module. So in this way, I can also have in the geometric fencing. So this is also an extension of the localization. This is some of the demos that using the visual localization and also the inertial localization and also the inertial navigation plus the binary sensor anchor. So this is very useful when you want to detect if two people is very close to each other in the COVID-19 situation. At that time, I'm having this demo to detect that if some people have a very close uh, distance, so it is very useful to improve the situation. And another thing is to detect the human activity because human activity relating to some very important information like if the elder people fall down or also maybe they are not in a very good situation. They are going to the toilet too many times, or they are not having their meals for several days. Okay, so this is the basic idea is that I detect the activity first, and then I detect the abnormal situation. So the human activity recognition is that sorry, this is not all the can I change another slide? Sorry, because this slide is already. Mm. Can you see my screen? Can you see my screen right now?
Yes.
Not at the
Yeah.
moment. Yeah, now.
Okay, so sorry that I will start from my publication, and this is the way that I can show that how the human activity can be recognized using the also the inertial sensor. So this is one research from the 2022 in the IEEE assess. And from this figure, this is the basic idea that how the uh, human activity can be recognized. So the basic idea is to using the wearable sensors like the smart glass, smartwatch, and also smartphone and smart shoes. And I detect the three coordinate XYZ information about the accelerometer and also gyroscope and magnetometer. And I do some pre-processing like the median filter, low pass filter. And then I use the feature extraction model training like the basic SVM, KNN, the random forest. These are all the basic machine learning and also the deep learning like the CNN and also transformer. These are all the modern learning model. And then I can get the output that whether I am working, running, and going upstairs, downstairs, and also I'm bicycling. But the problem is that maybe we might have a uh, very big challenge about the cross subject situation. So it's because that we have different habit and also different ways to wear our wearable devices. So one of the way I can improve it is to using the uh, Gini uh, parameter here in the random forest and actually inside the decision tree. So in this way, I can make the Gini metric to be more sensitive to the activities, but not the human habit itself. So in this way, uh, we introduce one new parameter that can calculating the different proportion of the in-class distribution and also the out-of-class distribution. So it improved the final cross-subject activity recognition. These A1 to A2 to A12 are all the activities like the walking and running and going upstairs, going downstairs. Okay, so these are all the open public data set that I have evaluation and found that in the small data set that we do not have many people and many activities, the traditional machine learning model is very efficient, but deep learning is not so good. And also for the cross-subject learning, the machine learning model is very good, and the best result is coming from our new metric that using the Gini parameter inside the random forest. Okay, and we also have a new privacy preserving human activity recognition from this year from the IEEE TIM journal. Is that the basic idea is to use the sound, but because you know the sound
Can I ask you? Can I ask you to slowly conclude your session? We have the time for questions.
Okay, thank you. The conclusion is that some of the preserving of the human activity localization and also the human activity recognition is to use the non-speak area of the sound, and I cutting out the audible area and using the inaudible area to do the activity recognition and also the localization information checking. So you can see that in the inaudible frequency, when I'm doing different activity, I can have the patterns for different, and also the inertial, so they are complementary information. Okay, so this is one privacy preserving, and we are still working on this area. And finally, I want to conclude is about the other people's research. Is that, sorry, just 1 minute. Yeah, this one. The trajectory is actually relating to the cognitive assessment. If you have like MCI or the other like Parkinson, maybe AD and also PD, your trajectory is actually having a biomarker. For example, you can see that for the normal people, we might just, if I want to do the activity from A to B, I will having the direct or normal trajectory. But if I having some problem with my mental health and maybe the physical health, you might have the pacing trajectory and also the lapping trajectory. And some severe case is that random trajectory. So tracing the people's daily trajectory from the location and also their activities is very useful to early detecting their state of the mental and also the physical. So this is my today's presentation.
Thank you very much. Wonderful. I'm
Thank
gonna
you.
stop.
Thank you.
I'm gonna stop the recording at this point.